Hello everyone. In this video, we will be talking about American options. Before we talk about American options, let me refresh your memory on European options, which we did already. So remember, if you go from 0 to the expiration time, a European option, you can only exercise at time N. So that's going to be the main difference between a European and an American option. The main difference is that European you can only exercise at this point, but an American you can exercise at any point, including the expiration time. And that makes finding the price a little more tricky. Here is the formal definition. An American call or put option with a strike price K and expiration time T gives the holder the right, but not the obligation, just like the European, to buy or sell an asset for the price K at any, this is the difference, at any time up to T. All right, let's do an example. The process is very similar to the method we use for European options or the binomial trees. It's very, very similar. Obviously, there has to be some differences, which you will see along the way. Consider a two-period model for an American put option where the initial value of the stack is $8, the strike price is 9, and you have 2 delta t for the time period because you have 2 steps, so you have delta t twice. And let's say that R is the continuously compounded interest rate, so such that this is true. So therefore, our goal is to find the option price. Again, keep in mind this is very similar to what you did in the European options. So let's do a tree first. All right, so we have the initial value of the stack is $8. And for the first period, the stack can go up by 100%. And this has to be given on the problem somewhere. Or it can decrease by 50%. And then in the next step, you can do the same thing. It can go to 32 or down to 8. This one can go up to A, and this one can go down to 2. Again, remember this is n equals to 0. This is n equals to 1. This is n equals to 2. Here we have the strike price is 9. And for a put option, remember the payoff function is k minus s, in this case st, but that was for the European, so for the American will be sn. So it's not st anymore. Okay. We also have the e of to the r delta t is equals to 5 over 4. And that t is equals to 2 delta t. All right. Now, if we look to the strike price, since we have a put option, if you exercise at this point, you end up with 0. If you exercise at this point, you end up with 1. And if you exercise at this point, you will end up with 7. Okay. Remember the notation we used before. This one is 1s1. This one is 2s1. This one is a 1s2, 2s2, 3s2, and 4s2. This is going to be useful in a little bit. All right, so if you recall the process from the Europeans, we had to focus on this part, and then this part, and then you go backwards until you end up here, and that's where you get the price. Okay. So let's focus on this part first. So this is what we have. You have 16. This one is 32. This one was 8. Then this was the payoff, 0, 1. All right, so we're gonna figure out 1U1. Here, the U represents the value of the portfolio at time 1. We need to use a different notation. You'll see in a little bit why. Now, you should stop the video and check that the value for B is equals to 1, which should be obvious because it goes up by 100%. And A is equals to minus 0.5 because it goes down by 50%. All right, so if we wanted to find the price at this point, then here we have the fee is equals to 0 minus 1 over 16 times 1.5, which gives you minus 1 over 24. Again, this is not new. You should stop the video and verify that this is the case. And then psi, remember, is equals to e to the minus r delta t times f of v minus f of v minus f of a over v minus a times 1 plus b. If we plug in the values, this gives you 4 over 5 times 0 minus 1 over 1.5 times 2, which give us 16 over 15. Okay. So then the value for 1U1, which is this one, is going to be equals to phi s plus psi, the exact same thing we did before. So this is minus 1 over 24 times 16, because that's the price of the stack at this point, plus 16 over 15, and this is equals to 2 over 5. Again, you should stop the video and check that this is the case. Recall that we have two ways to do this, or you could have done this to get to the same part. Remember that Q, the martingale probability, was equals to e to the r delta t minus 1 plus a divided by v minus a. And if we plug in the values, this would be 5 over 4 minus 1 half divided by 1 plus 1 half. And you should check again that this gives you 1 half, which implies that 1 minus q is also equals to 1 half. So remember that the other way to figure out the pricing was using conditional expectations. So U1 by definition is equals to e to the minus r delta t times the expected value with respect to the martingale probability of f of s2 given the information after time 1, which in our case this means that 1U1 is equals to 4 over 5 times 0 times 1 half plus 1 times 1 half, which are these values right here, and this gives you this, and then you simplify, it gives you 2 over 5. So it's up to you if you want to do it using this method or this one. All right, so now let's move to the next part of the tree, which is this one, and do exactly the same thing. So let's go to the next page for that. The second branch looks like this. This one was 4, was 8, and 2. This one was 1. This one was 7. And we need to figure out 2u1. Right, so we do the exact same process. Here, phi is equals to now 1 minus 7 divided by 4 times 1.5. This gives you negative 1. You should check that. Then psi is going to be 4 over 5. 1 minus 6 over 1.5 times 2. And this is equals to 36 over 5. Hence, we end up with 2u1 is going to be minus 1 times 4 plus 36 over 5. When you simplify all of this, you should end up with 16 over 5. Again, you should check. Or you can use the conditional expectations, and you do that. 2u1 is equals to 4 over 5 times 1 times 1/2 plus 7 times 1/2. And this is equals to 16 over 5, which is exactly the same thing. Okay? All right, so let's regroup and see what we have. If we create a new tree, this is what we end up with. We start with the number 8 again. Remember, this one went to 16. This one went to 4. This one went to 32. Then it went to 8. And then this one went to 2. Okay? All right, so here, what we're trying to figure out eventually is B0, B1, and B0, that's what we want to figure out at the end. This is what we have so far. We end up with 2 over 5 in here. And that's what we call U11. And then 16 over 5, which is what we call U21. Okay. Now, if this wasn't a European option, then the next step will be to use these values to figure out the answer. But since this is not European, you had to worry about something else. Let's say that you want to know what will be the value you exercise at this point. I'm going to use the W for that. So we will call this 1W1. If you exercise at this point, the value clearly is 0. If you exercise at this point, which we call 2W1, then the value is 5. Okay? So therefore, to determine the values, we're going to do B1 will be the maximum of W1 and U1. So therefore, 1B1 will be the maximum. And this is pretty much the main difference between European and the American when it comes to the computation. 1W1 and 1U1. Or in our case, what is the maximum between 0 and 2/5? And clearly the answer is 2 over 5. Then if we do the same thing for the other one, 2B1, this will be the maximum of 16 over 5, which clearly the answer is 5. Again, convince yourselves that this is what you get. You should stop the video and compute this on the side to make sure this is what you get. All right, so from here, therefore now we can focus on this part and finish the problem. This is what we will end up with. So the last three will have, you have A in here, then 16, 4, and now the payoff is going to be 2 over 5 for this one and 5 for this one. And we use the exact same process we did before. So therefore from here, phi is going to be 2 over 5 minus 5 over 8 times 1.5, which will give you minus 23 over 16. Again, you should check that. And then psi will be 4 over 5 times 2 over 5 plus 23 over 5 divided by 1.5 times 2. And when you simplify all this mess, this is a 392 over 45. You can just use decimals too. So therefore from here, U0 will be minus 23 over 60 times A plus 392 over 45, which is equals to 54 over 25. Remember that you have another choice using conditional expectations, or U0 will be e to the minus r delta t times the expected value with respect to q of b1, which in this case will be 4 over 5 times 2 over 5 times 1 half plus 5 times 1 half, which is 54 over 25. Well, this is not the final answer yet. If you remember, we used to call the auction price X, and X is just B0. So B0 is going to be the maximum between U0 and W0. And W0 in this case is equals to 1. Why? Because the strike price is equals to 9. So 9 minus A will give you 1. So therefore this will be the maximum of 54 over 25 and 1, which is equals to 54 over 25. And this will be the option price. This is something you have to worry about the European, but here this is very important, because if this value is less than this one, then you can exercise right at the beginning and make free money right from the start without even waiting for anything. Another thing to remember about to notice about the American options is that for the European, remember you have a put-call parity. You don't actually have that for American options. The best you can do is something called a put-call inequality. Okay. And the put-call inequality looks like this. So it's better than not having anything, but it's not a put-call parity. And also something that is very important is to notice is this: less than 10% of American options are actually exercised. Okay. Like I mentioned in class before, to figure out the precise value of an American option is way more tricky than a European option in real life. All right, in the next page, we're going to get a little more theoretical. We're going to discuss something called stopping times, and the point or the idea of a stopping time, like the name suggests, is where should you stop? And by stop here, it means where should you exercise to make sure you get the maximum profit. The next topic is stopping time. So what is a stopping time? A stopping time is usually denoted by tau, And a stopping time is nothing more than the exercise time when you decide to exercise the option. We will be focusing mainly on optimal stopping time, which will be denoted by tau star. And optimal here means that will be the time where you decide to stop so you can get the maximum possible profit. Tau star is actually a random variable that depends mainly on the price trajectory. For example, if we use the information from the last example we did, remember in the last example, this was the trajectory. You start in A, this could go to 16, or then it could go to 32, back to A, this could be 4, up to A, and then finally 2. Here we technically have 4 trajectories. This is one, this is the second, this is the third one, and this is the fourth trajectory, which we actually have names for that before. Like this one was 2s2, 4s2, and so forth. In the previous example, this was equals to 0. That was the payout function. This was equals to 5. And then the well function at this point was 16 over 5, which is around 3.2. And here it was 2 over 5. Remember that the value for k was 9, and the payoff function was equals to k minus sn plus. Also, remember that we have technically 2 periods, n equals to 1 and n equals to 2. So let's look at this one by one. At time equals to 0, the payoff function is equals to 1, which clearly is less than the value of the option, which was 54 over 25, which is around 2.16. So therefore, at this point, definitely you don't want to exercise, because if you do, you will lose $1.16. You should check that. It will be helpful to name the trajectories like this. This will be up. It will be up, up. This is up, down, which is the same thing as down, up. So this is down, and this will be down, down. So those are the 4 trajectories. So at n equals to 1, we have u star. So I'm going to put a star in here. From here, the payout function will be now 9 minus 16 plus, which is equals to 0. So this implies that the put option is out of the money. So therefore, at this point, you do not want to exercise. So no exercise. Okay? All right, let's look now at n equals to 2, which will be this part. So let's consider first the case where the trajectory goes up and then goes up again. So this will be u, or up, up. So clearly at this point, the put again is out of the money. And here, once you get to this point, there is no place to go. This is the end. So this is called a dead state. So this will be a dead state because there is no place to to go. So if you end up in that situation, then the optimal stopping point T of omega, which in this case is T omega up, is equals to infinity. So infinity is always going to denote the dead state. In that state, again, it means you will not exercise, you will just let it expire. All right, so what about the next case? What will happen if it goes up, then it goes down, which will be this case? So here is important, it goes up first and then down. If that's the case, then the path here will be omega is equals to up and then down. And then in this case, the stock is on the money. It's $1, but it's on the money. So therefore, this will imply that you should exercise if you enter at this point. Okay? So therefore, that will imply that the optimal stopping point here, or time, if it goes up and then down, is 2, which means you should stop at n equals to 2. That's what this 2 means. Okay. Now let's look to see what happens if it goes down first, which will be again n equals to 1, which will be this case. So let's put a starting here, just like we did in this one. And this is actually the most tricky then. In this stage, or in this path, or in this trajectory, if it goes down first, here you have to be very careful. If it goes down and you exercise right away, then you automatically make $5. That's the payoff. But you keep going, then from $5, the value of the option becomes 16 over 5, which is 3.2. And it is true that if it goes down, then you will be making $7 instead of 5. But if it goes up, then you will only make $1. So there is the potential to make more, but there is also the potential to make less. So if you exercise right now, you will get $5. So therefore, you should exercise at this point. So therefore, what that means is that the optimal stopping time, if it goes down and then up, should be the same place as stopping if it goes down, and it should be 1. Meaning that if it gets to this point, you should exercise right away, because after that, yes, there is a chance you will get more, but there is also a chance you will get less. Therefore, in this particular example, the values for tau depends only on this, whether it goes up or up, down, up, or down, and this is pretty much the sample space. Another way to look to tau star is the following. The possible values for omega, as we saw right now, are this. And then the value for the stopping time, remember, was infinity, which means you never exercise. Remember, this was a dead state. This one was 2, this one was 1, and this one was 1. Notice how the value for 0 is now part of the sample space. And the reason is that it was obvious at the beginning that you don't exercise at n is equals to 0. That's why n equals to 0 is not part of this. But in other variables, it could be part of the stopping times. Let's look to something now that it may look like a better stopping time, but you will see that it will turn out to not be a real stopping time. Okay. Recall, this is what we have for the trajectories. We can have up and then up, up, or we can have down. You can have up, then down, or down and then up. We could have down and down. And here you will see that these two are not necessarily the same, as you will see right now. All right, so if we introduce a new variable, let's say row, obviously, if we end up in this place, which means up, up, you will stop right away. So you will exercise at this point. You already know it's gonna go up and up, so you're gonna lose everything, so you will stop there. Well, let's say that you have now row of UD, which means you know that it went up and then it goes down. So if this is the case, well, then you will stop at 0 also. Well, the next stage will be this. If it goes down and then you know it's gonna go up after that, well, then you will stop in step number 1. Why? Why is this 0 and this 1? Well, if you know, and this is the key, notice how I keep saying if you know that the trajectory is gonna go like this, goes down and then up, well, therefore you wanna exercise right here, because if it goes up, then you're gonna lose the money. But this one, if it goes up first, you're gonna lose, and then if it goes down, you may get something here, but therefore that's why you wanna stop it right away. And obviously, if it goes down and then down, you know that's what's gonna happen. Well, you will wait until it gets here, because this is where you will get the maximum. Remember that this one was 7, was the maximum you could get. This one was 1. This one was 0. This one was 5, and this one was 0. So obviously, if you know it's gonna go this way, well, you will stop it right here at time equals to 0. If you know it's gonna go do this and then this, well, you will stop it also right here in 0. But if you know it's gonna go down and then up, then if you stop here, you will get $5. And if it's gonna go down and then down, then will you stop it until step number 2. Well, there is a issue here, a big issue, that this requires that you know what's gonna happen, which means it requires that you know the future. And if you know the future, then you will not have to worry about anything. So therefore, these are not stopping times. So these are not stopping times. And the reason is because they require that you know the future, which if you knew that, then there will be no need for you to try to figure out where to stop. Now let's look at a more formal definition of what a stopping time is. So a random variable tau, which depends on omega, taking values between 0, 1, 2, all the way to infinity. Remember that infinity is the dead state. Is called a stopping time with respect to the algebra A sub n if the following event, tau, such that t out equals to n belongs to the algebra. Remember the a sub n from the previous sections is equals to the information that you have up to time n. Or another way to look at it is this: tau is a stopping time if having the information a sub n, we can say at time n whether the event at tau of omega equals to n happen or not. So this is another way to look at a step in time. So tau is a step in time if once you have the information up to time n, you can say specifically time n whether this event has happened or not. We made two small notes here. So note number one, tau is independent of the future, which means that you can not look ahead. So you have to make your decision based on what you know at time n. Note number two, if you have the state tau of omega equals to infinity, notice that this belongs to the algebra. So what this implies is that if tau of omega is not equals to n for n equals to 0, 1, 2, all the way to n, which is the last step, then that means that tau of omega has to be infinity. So once you get to the end of the tree, remember, once you get to this point, if nothing happens, then you're going to have to go with infinity. All right, let's look to the next illustration related to this. All right, so we already know that omega is equals to this. It was up, 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 down, down, up, and down, down. Okay. So then we're gonna create this sequence. This is the algebra that includes just the empty set and omega. Remember, omega is this. Let's say that A1 is equals to the algebra of that contains the empty set, omega, A, and A complement, where A is equals to just it goes down, up, and down, down. Okay. And let's say that A2 will be the algebra of all the subsets of omega, including the empty set. Okay. So we have, using this information, that the following set omega such that tau star of omega is equals to 1 is equals to du or dd. Okay, we saw that in the last example, which this is equals to A. And remember, this belongs to A1. All right, then if we look to this next event, omega, such that tau star of omega was equals to 2, the only one we end up with at that time was UD, and this clearly belongs to A2. Okay, and then the last one is omega such that T star of omega is infinity, which this one was UU, and this one belonged to A2. So clearly, you put all of this together, this satisfies the definition of stopping time.